So in this case, we are going to consider as a continuation working with the construction and also interpretation of a circle diagram. We managed to work with the basics from the previous class that we had. So in this case, without wasting time, we want to consider a typical question that we can use to actually construct the diagram, which is our circle diagram in actual sense. So I need us to consider the steps that we are going to follow up in order for us to have the diagram and also to answer the following questions that we are given. So the question that we have was to draw a circle diagram for a 20 kilowatt 6-pole 400-volt 3-phase induction motor using the data below. All given values are line values. The values that we are given here are line values. So we had a no-load test with its corresponding values. We also have a locked-rotor test with its corresponding values. So remember what I said, guys, our no-load test, which simply represents what? An open circuit test. So meaning to say we are given V1, we are also given the current, which is at no load, then the power at no load. The locked rotor test, which represents the short circuit test. Meaning to say we have got the voltage for the short circuit, we have got the current for the short circuit. We also have the power for the short circuit. So the given information differs. It differs from other information. They might give you the corresponding power factors, where from the power factor, you can calculate or you can determine the corresponding phase angles. So assume that the stator copper loss equals the rotor copper loss at standstill. Remember, this effect of the rotor copper loss equals the stator copper loss equals the rotor copper loss at standstill. It affects the point of E, where we are going to mark the point E. So this one is going to be the last part when we have the semicircle here at point E. Remember, I talked about that. When it is like this, the point E will be halfway because these two, they are equal. So you find E being halfway of AF. So we are going to see that one later on our presentation. So we must take this one into consideration. Using a scale of 1 centimeter equal to 5 amps, determine the following from the circle diagram for maximum output condition. You are given a condition to use or to work with for maximum output. So we are going to use that one later on. Remember from our diagram, as we had the steps that we referred to before, the conditions that will be for a full load, for maximum output, they are going to affect the line LK. And I talked about that line LK, that a lot of things can be determined from that line. So we are going to see that one at the end. Do not worry about that. So guys, let us see. As I stated in the previous class, we saw that the reference is the vertical axis, which is OV, and from that OV, we must have the corresponding line, which is taken from the angle that is for the no load and that must give us the no load current. It must be taken from the no load current. All right. But remember, we said as the distance, as a vector from the graph, that is point O to its referred value, which is O bar, like that. So meaning to say, guys, let's start with that condition first for the no load. So that will be your step one. So for no load, we are going to need its corresponding angle there. We are not given the power factor. They gave us the power, the current, and these are line values, remember. So remember from the power, the formula, guys, that I gave you before. Okay, I just hope these formulas, I did not erase them, but remember I mentioned something about these formulas here. All right, I erased them. When we calculated, when I was talking about this calculation of the angle there from the three-phase condition and its power, which is equal to the square root of 3, the line voltage, line current, times our power factor. So we ended up with a formula, which was the power factor can be calculated from power over square root of 3 times voltage times what times current. So meaning to say, when we are dealing with the one for the no load, we must consider of the no load, meaning to say we must have the power for the no load, the voltage for the no load, and also the current for the no load. So that's it, the power. We are given according to our information, that's 1.8. So guys, just take this information, this one, as it is. All right, because of where I wrote this formula, just take it as it is. So that was 1.8 kilowatts times 10 to the exponent of 3. The square root of 3, our voltage there at no load, remember it was 400. Then the current, it was 15 amps. Okay, so that was going to give us something like 0.173 and so on and so on. Remember, this is our power factor. What we need is the angle, the phase angle. So therefore, our phase angle from arc cos, remember we're dealing with cos, so it's going to be arc cos on your calculator of this decimal as it is. Just let me do this. All right, so let's say you've got your value like this. That's 10 to the exponent of 3 over the square root of 3. Okay, we're going to multiply to 400 times 15 like this. So you're going to get this, then simply shift cos, that is arc cos of the answer that you obtained. All right, so that's 80,023. Okay, 0.25, something like that, which is approximately 80 degrees. Because guys, we cannot like indicate exactly this angle of 80.03. So it's just going to be an approximation just around 80 degrees there. All right, so that's the angle that we have for the no load. So for the no load, the first thing, you're going to need the angle. We got 80.03. Okay, then we are going to need the vector or to O bar this one, which represents what? The no load current. And that vector, we said it is what it represents over the scale. It represents what? The no load current over the scale for us to have the exact measurement for that. So the no load current is there. That is 15. All right, so we're just gonna need to substitute. All right, so that is 15 over what? The scale, remember they told us each centimeter represent 5 amps. Each centimeter, 1 centimeter is equivalent to 5 amps. So you're just gonna divide by 5 by the scale, 5. So that was going to give us 3 centimeters. So a vector in the measurement that you're given, centimeters or millimeters. the current was measured in amps. So we cannot represent 3 amps, guys. How can we measure 3 amps on a graph? But how can we measure 15 amps on a graph? But we can measure 3 centimeters. It is something that we can just use our ruler to measure that one. So wherever we see 3 centimeters in this corresponding vector, it is representing what? The no load current. That is it. So that is the major part that you are going to need for the no load. So that is what we're gonna need. These two things. You can represent them graphically. With these, we can represent graphically. The angle is there. Remember, from the voltage, you measure your angle. Then you just measure 3 centimeters. So that's it. The same thing is going to happen for the short circuit. The same thing, guys, is going to happen for the short circuit, which is our locked-rotor part. The same thing is going to happen for the short circuit. So for the locked-rotor, all right, so this one is going to be for the locked-rotor test, which is our short circuit. So in this case, we are going to need what? The phase angle. Just like the previous case, we do not have the power factor, but we have got the power, the current, the voltage, and these are line values. So still we can have the formula that we used before, but this time we are simply going to use what? Short circuit. So this one will be just short circuit. Just going to change our formula there into short circuit. That is the idea there. So this one, guys, is just a repetition. So this is short circuit, short circuit, short circuit, short circuit. So already these values are given, the power. Just want you guys to take these values as it is, power, voltage, current. So that was 3,9 for the power, 3,9 kilowatts times 10 to the exponent of 3, the square root of 3. The voltage for short circuit, we are given that was 140 times the current, which was 38. So that's it. So that was going to give us 0, 0.42324, something like that. All right. Just like the previous case, arc cos of that value for us to have the angle now. So that was going to be 64,96, something like that. So indicating these guys is going to be difficult. So just going to approximate on your measuring there, just approximate 65 degrees, something like that. Okay, so do not worry about that. That's approximately 65. So this one approximately 80, and this one approximately 65. So we have got the angle for the short circuit, which is approximately 65 degrees. Then the corresponding vector, this one was O to its referred value, which is O bar, like this one. But what about the short circuit? Remember, for the short circuit, I said it is going to be taken from point O to A. You'll be having your short circuit current here. This is where you're going to be. Your phase angle for the short circuit. Then from point O to point A, this vector represents our short circuit. But it is a condition of the short circuit where we are assuming normal voltage being used, normal conditions being taken into consideration. So meaning to say, we must calculate this one first before we consider its vector OA. And how do we calculate that? All right, so those are the steps for you to calculate the vector OA. So you're going to need by finding the short circuit current, which is a normal consideration of the given voltage. So we say the formula is short circuit current times V rated over what? V short circuit. Remember your formula, guys. Your short circuit current is given. That's 38 times our V rated of the induction motor, 400 volts. So we have got that one as 400 over V short circuit, which is our short circuit voltage is what? 140. So that's it, guys. Remember those steps. I talked about this before. So that was going to give us the corresponding short circuit at the normal voltage, that is 108,571 amperes, which is the one that we need to determine the corresponding vector here from O to A, where that short circuit current lies. As we can see, just like before, where the no load current lies, you must find that corresponding vector. So our short circuit current lies on vector what? OA. So OA will be what lies there over what? Over the scale, just like that. So what lies there is our short circuit current at normal value, which is 108.571 over what? The scale. 1 centimeter represents what? 5 amperes. So we're going to divide by 5. So that was going to give us approximately 21,714 centimeters. So that's our vector OA. From what? The short circuit current, we have got vector OA, which is, like we say, 21,714 centimeters. So this is representing our short circuit current at normal value, but as a value which can be graphically presented. We are just taking away the normal values that we are used to. It was a normal value as a current, but we want to avoid that. So with these, we can now put into consideration our graphical part. So I want us to have our graphs. And as part of the graph, we are going to start by presenting these two for the no load and for the logged rotor test. Those are the major parts that you're going to need. And with this information, guys, we're going to see that everything will be clear. All right. So as part of our graph, all right, so this is what you're going to have. These are the instruments that we are going to need as part of our construction. We are going to need the ruler for our measurements. All right, then the measuring part, guys, in terms of our angles, we're going to need our protractor and our compass. So that is it. With the angles measured from the reference, all right, so let me just have this one as my reference. I'm just gonna, all right, let me just put these ones aside. So remember, the vertical is our reference. So I'm just gonna put the reference on the vertical. Let's see if we are going to win. Let's see, guys. We must definitely win in this case because we need to understand all the basics. So let me just take this one. Vertical and horizontal part. Let's say we've got something like this. Okay. So this is what we are going to need. All right. Let's just hope it is clear. We can also see the line. So this is our vertical part. And along the vertical line, we are going to have the O as our origin. All right. And this is our V voltage, your terminal voltage there. So this is your reference. The vertical becomes your reference, meaning to say whatever that you're taking must be from what? From the reference. This is the major case. So what we need from the reference is the angle in between the voltage and current. Remember, voltage and what? And current. So the current that we're talking about is the no load current. The angle in between is 80,03, which is approximately 80 there. So let's say this is how it was supposed to be like. Where in between you have got 80.03 degrees. So you must measure from the vertical, because your vertical is the reference. It's not the horizontal this time. Remember, guys. So this is what was going to happen. Since we want to measure this, let us just rotate. So we must have this in a vertical line at the origin. Okay, so this is our origin here. So make sure that this plus here, where we have got the plus, this like this line that is going to 90 degrees, and this vertical line, they are on the origin. So you place this one on the origin like this. Okay, so make sure 180 degrees and 0, this one, are covering the vertical line. Then the 90 degrees, 270, this one, is on the horizontal line. Then you can measure your angle. So the angles that you're taking are like this, from V going this side. So we are moving in the clockwise direction. So you take this angle starting from 0, 0, 10, 20, 30. Those are the angles that you're going to take from 0 going this way. So 80, 3, guys, it's just approximately at 80. You see where 80 is? Approximately, you just measure that 80. You mark a point at 8, which is you go straight where 80 is. Straight, that is corresponding to that 100 there. Where 80 is, just an approximation, that one, where 80 degrees is. So that is, it was going to be like this, where 80 degrees is. Okay. You just mark the point, then you can draw the line from there. This is our 80 degrees. From where? From here to here. This is 80 degrees. 80, 3 degrees that we're given there. So the angle that we are given, all right? So let me just try to, right? If I do this, it affects, I want to, okay, let me just leave it the way that it is like this. So this part that we are given here, representing 80 degrees, is where the current of a no load is supposed to be. Like we have got our no load current. But we are not using this as no load current. We are using it as a vector, remember. All right. So that is the idea there. So let's go back and take our 80 degrees again. Let's just have this one and finish. So you say it like this. Okay. This is where we have got our 80 degrees. You can even just mark a point where you see that 80 degrees, all right? You just mark a point. Yeah, I don't want to draw a line. I just want to mark a point, all right? Okay, so this is the point that I'm talking about here. So let's say you marked a point, because the way that we are constructing, guys, might differ. Let's say you marked a point to show that from here to here, it is 80 degrees. Then you can simply use your ruler now to join from the origin to that point. But you just need to extend a little bit. This is construction, guys. It's not like a drawing. It is just a construction. So just also allow a smaller space of that construction. Okay, something like this. So you're just going to need something like this. All right, so that's our 80 degrees. So let's just join from the origin. From the origin going through, you must pass through that line. all right, like this. Okay. So, okay, this one is just a little bit, but you must just pass through that line like this. So here it is along this line, along this line, that is where we have our 80 degree, along this line. So it represents what? The no load. So that is our no load phase angle, this one. It was supposed to be no load current represented, but graphically, we are not going to represent it as no load current. We are going to represent as O to its referred value, which is O to O bar, which is 3 centimeters. So along that line that you have drawn this one, measure 3 centimeters from the origin now. You measure 3 centimeters as we are given there. So 3 centimeters according to mine, guys, here I'm just going to use according to my graph here. 3 centimeters, that's approximately at this point. So I'm just going to mark aside, all right? Does not allow me to mark aside. I just hope, guys, it's not going to affect. All right, here it is marking, but here it is not. All right. We need 3 centimeters. So it is here. Okay. 3 centimeters at this point. So this is where my 3 centimeters is at this point. So that point is my point what? O bar, this one. Remember, this is the origin. So that is the referred value now, which is our O bar like this, which represents what? Our no load current as a measured value, something that you measure from the graph. You get 3 centimeters. From the graph, you get what? 3 centimeters. So when you take it back to that consideration, you want to calculate the exact no load current. You just take, okay, it is 3 centimeters. But remember, they said each centimeter represents 5 amps. So if it is 3 centimeters and you want to get the exact value, you must multiply by that. You multiply by 5. So 3 times 5 gives us what? 15 amps, which is exactly the one that we're given before the 15 amps here. There is a graphical part. There is the exact value. All right. So that is how we interpret that, guys. So that is for the no load. We have for the no load. With the same understanding, we must do this for the what? Short circuit. But as we have got this part of the no load along this referred value of O bar, this one, we must have a horizontal line parallel to the horizontal axis. Remember this line, okay? Let's go this one, from this O bar, this one, this line. It is parallel to this line, these two, maintaining equal distance. So it must maintain equal distance in between. So you just take that point O as it is, you draw a horizontal line, straight horizontal line at that point. So approximately that's there at point O. So you're gonna take straight horizontal line there from O like this. So this is it, all right? These are the steps that you need. All right, so with this one, let's go now to the short circuit. I just need, let's hope this one is gonna allow us to reduce some of these lines. So this one, again, it is a construction. So don't worry about these lines that are even extending, okay? But you can erase, guys. You can erase, okay, this line is extending, so you can just try to erase a little bit like that, okay? That is a normal presentation there. This is no load. We are done with the no load. We go back to the short circuit. Our locked rotor test, the angle 65 degrees, the one that we approximated from 64.96. We saw that, guys, to measure 64.96, very difficult. So just approximate to 65. So we must measure 65 degrees from the reference line, just like the previous case. Going this side, you measure 65 degrees. So let's put that one again on the what? This part here, you put it on the origin. So it must be on the origin like this. All right. So you must close this part 180, and this line must cover this one of the horizontal for 90 degrees. So we need angle 65. So from 0, like I said, in clockwise, 0, 10, 20, 30, 40, 50, 60. This is 70. So 65, it's in between 70 and 60 here. This is where we're going to have our 65. So in between, you just mark a point there, or just draw a line direct. All right. So this is here. I don't want to draw a line. I just want to mark a point first. All right. So that point is the one that we are going to need, this one. This is at 65 degrees. So what it simply represents is that from this line going to this point, the angle in between is what? 65 degrees. So as we must now indicate it properly, how we now join from the origin, passing that line, extend that line, pass through that line, all right, from the origin. So let me just use this one. All right, 65 is just going to be something like this. We extend. This one is supposed to be extended, as we saw, even from the sketch that we had on our introduction. This one is that's the longer line that you are going to have. So it must be extended. I just hope, guys, it is going to allow us to have this done. That was 21 centimeters. So I need something like around 21 centimeters, guys. 21 is there. 21, 22. All right. So you must have it according to that measurement. Extend. If it is 25 centimeters, extend up to that one. All right. So here's 20. 21, so approximately along 21, but make sure that you pass through the what? That point, this one. You must pass through this point. Let me go back. Yeah, you must pass through that point of 65 degrees, all right, from the origin. So something like this. So let's just hope, guys, this one, our instruments, they're going to allow us to finish, because the way I'm seeing it is going to be difficult with the instruments. Our instruments, they limit us, meaning to say we are supposed to go back to our traditional way of having, using like the board or something, just a sketch. I just hope it's going to give us the exact thing that I need here. Anyways, so this is it. You have got this line representing an angle of 65 degrees, which is the angle that was what? For the short circuit. So the angle up to this line here is the one for the short circuit. So that is the first angle that we had for the short circuit, which is our 65 degrees. So don't even bother about indicating to say this is equal to 65. They will measure those angles. But if you want to just indicate, but they will measure those angles. So don't even worry about indicating. The examiner will be having all those instruments. That is their job, guys. They must measure everything to see that you are doing the exact thing. So with this part, with your short circuit, along that angle, along this line, that is where we are going to have our short circuit current of those normal conditions. So it is between what? Voltage and current. The phase angle always between voltage. So this is supposed to be the short circuit current, this one. But we cannot just measure current, guys, here. What we can measure is the length. So that is the length from O to A, the length OA, vector OA. Remember 21.714 centimeters, which is approximately 21.7 centimeters. Guys, we cannot measure these ones. So you cannot have exact values. So you just have approximate values. Even your answers, do not worry about them. They'll be measured, they'll be marked according to that. You must make sure that your answers are in the range. So we need to measure 21.7 centimeters along that line. So here, according to my graph here and my ruler that I'm using here, 21.7 is approximately, this is 21, 22, 21.567, approximately there, right? I'm just going to mark what is happening, what is corresponding according to mine on this side. So, all right, why is it like it's not marking, guys? I must have that point indicated or marked, all right? It was somewhere there. So this is where we have got our point A, from O to A. So you mark that point A. So OA, this one, represents the short circuit current at normal, assuming normal voltage. So that is the exact idea of that part. So these are the basic part that you must have. That's the basic part of your diagram. This one is the basic part. The angle, corresponding length of the vector, angle, corresponding length of the vector. Then with the point O, with the point A, what we are now going to need, we can go back to those steps after having your points. What are we going to need? We are going to need the semicircle, and that semicircle, before that, we must have the point C, which is, in order for us to have the point C, all right, we are going to need it from the output line. The output line is this O bar to point A. That's our output line. So let me draw the output line, join. So you're going to need to join those two. That is from O bar, the referred value, to point A. So that is to point A. So let's just hope everything will be clear at the end of the day. Something like this. So these 2 points are too close, guys. They are too close, like we might have a challenge of joining them. Or let me just do this. There's no need of us using a ruler here. Let me just find a line, join these two like this. So you are using your ruler there. But here, as we can see, guys, using a ruler was difficult. So you join that part, okay? From point O bar to point A. So that line, remember, it represents, it's a special line that we talked about before. That's our output line. So we've got what? The output line. Okay, which is from O bar to A. On the output line, you are going to need halfway of that line. That is where we are going to construct 90 degrees. Okay, let's go back here. Can make sense on this part. In order for us to have the point C, this one, we must have a perpendicular bisector of this one, O bar to point A. we must have a perpendicular bisector. Remember, bisector divide into two equal parts. Perpendicular, it must be at 90 degrees. So we need half of this bisector, half of that. So according to your line, guys, you measure the distance between those 2 points that you are given, the distance between, then you have to divide it by 2. So according to this line of mine, it was something like, this is something like 20, 24, 23.5, 23.4 centimeters. So you must use the measurement, guys. This one, you must take it from your graph. All right. You must take it from your graph. Then you must find half of that. So if I'm to take this one according to what is happening here on my graph is 23.4 or 23 point what? 23.5. Approximately that 23.6. So let me divide that one by 2 and see. All right. You use what is happening on your graph. Here, I'm taking the measurement, not from the exact measurement, but from this graph that I'm using here so that I can find the exact half. So I'm going to need 11.8. That is the half. All right. So I'm going to need 11.8. So let's see where 11.8 is going to be. Let me change this one from this point, 11.8, somewhere there, here, 11.7, 11.8. So according to my graph in this case, 11.8 is somewhere there. That is where I have half of the line that I was given, this one. This is halfway. It is supposed to be halfway, midpoint, this one. It is supposed to be the midpoint of what? Of O bar to A, the midpoint. With that midpoint, you must construct 90 degrees along that to this line. So how do we construct 90 degrees? We measure it. So we are going to take our protractor like this. What you do is that you must have, this is now like your reference line. It must be along this line, this one, along the output line. So along the output line, so let's do this. We must be along the output line, something like this. So this one at the midpoint, where at that point here at the midpoint, you place it at the midpoint. Then 90 degrees is already clear, guys. Let us just be, must be a straight line, this one. 90 degrees is already clear from there. All right. The 90 degrees that we want is already clear. The 90 degrees is the one that we are seeing straight on this one. 90 degrees, this one, the one that is written 90, the 90 there. Remember, I mentioned 10, 20, 30, 60, 90. So where we see the 90, we're just going to mark a point there. All right. It goes straight to that point that we want. So in this case, let me mark my 90 degrees. All right. So this is where I have my 90 degrees. So I must join that from here. This is my 90 degrees. It is at this point. So I must join from that midpoint of our output line. All right. From the midpoint of the output line, something like this. The angle that we are going to be having there will be at 90 degrees. So guys, it's just going to be a lot of things, but do not worry. It's how it's supposed to be like. So like this. Okay. So let's also try to extend, all right, like this. So this will be 90 degrees, this line. So you must join this one and try to extend it because there are some adjustments that are to be done. So make sure that you extend that line. So this line that we have just drawn, this line, where it meets with the output line, these two, they meet at 90 degrees. Remember, it was drawn, taken at what? At 90 degrees from our protractor. So this is at 90 degrees. But we are worried about what? The point C. Remember, we want to have the point C. So to have the point C, we are saying where that bisector meets the referred line, this one, of O bar, this one line, where these two meet, that is where we are going to say we have got our point C. So that is our point C here. All right. So you must take note. There's a distance in between here, which is exactly the same throughout. We talked about this, representing those constant loss. That is the idea. So we have the point C. What is the major part of us having this point? What we are looking for point C so that we can construct the semicircle. In order for us to construct this semicircle, because I said C is the center and the radius is C to O by that one. That is our radius. Whilst C is the center. So what you're going to need in this case is your compass. You're going to need that compass here. The needle point, you place it at C because C is our center of the circle. So C, remember, is our center, this one. So we are going to need the needle point at C here. Then you open the distance to the A, the O bar, that one, which is what? Which is representing the radius, because we are saying this is the radius. So guys, our instruments now, you see, they are limited. So in this case, let me try to see if we're going to go back to this state that it was before, because once we change this, it's going to affect also our values. So anyways, let's see. Let's see again. All right, so let's try to have it like this. So if we are to consider, like what I was saying, it's from what? From C, all right, to this one, okay, something like this, to the point O bar, like that one, as our radius. With this distance, you can draw a circle, but we need what? A semicircle with like this. So it must get to the point O, to the point A. This is to show you that this is exactly done. If it does not pass through that point O, the point A, then it means something is wrong. But under exam condition, it can happen that it's slightly, maybe just slightly a piece. Yes, it can happen because remember, guys, that these measurements that we are working with are approximations, and somehow you might just do a smaller mistake. Do not worry about that. Let it be exactly between those points. But if not, then you are not supposed, guys, to change everything. You're just gonna work as it is, but it's supposed to be like this. So as we can see, we have got a semicircle drawn. So the needle point at C, you open to what? To this O bar. Is the radius, then you draw your semicircle to the point A. So it must reach point A. At least that can give you a relief in exam to say, this is exactly what I'm doing. I'm in the right way. But if it does not happen, maybe it is slightly along that point. Do not worry. They will mark according to what you are having there. All right, so that is about the semicircle. We have our semicircle. On the semicircle part, we can see the effect from C part, this line here that is going to the semicircle. That point where it reaches the semicircle is important according to the conditions. According to the conditions, is it on a condition that we are dealing with maximum torque? Is it on a condition of full load? So we are going to talk about that one later on. But what we need is to locate the point E. After the semicircle, we need to locate the point E as part of our steps here. This one. To locate E and also to draw that vector from O bar to E, conditions must be put into consideration. So in this case, there's a condition that they told us about the copper loss and the rotor copper loss at standstill. That is where it plays a role, this part. Remember, I said this part assume that copper loss, the stator copper loss equals the rotor copper loss. It affects E, the position of E. Why the position of E? We talked about this, guys, to say along this line, all right, let me extend this one. This one is supposed to be extended. All right, if you extend that line from your graph, all right, along that line that we have extended, if we take it vertically from A, all right, from that A there, we take this one straight going down. All right, let me try a little bit, increase this one. So we take this one straight at A going down vertically, supposed to be vertical at 90 degrees. It must be at 90 degrees like that. It must be, so you must take this one straight at 90 degrees. Okay. So as this line goes, it is actually supposed to reach the origin. Let us go to the ground. All right. Let's take this one to the ground. Like this. This line that we have from A to the ground there, that is A to G. Remember from our previous presentation, that was A to G. If you still remember here where I was talking about this. From point A to G. And F is on the referred line, this one, referred, this F. So meaning to say, we also have the point F on this referred from the O bar, this one. From the referred line, we also have we have got the point F that we do understand. We can mark that point. We have got that one, guys. It is something that is direct that we can mark. So along this line, the referred, this one, where it meets, with this one, that is where we've got what? Our F. So we are much considerate about the distance AF, this one. This is the one that helps us to locate the point E. FG, this one, do not worry about this because FG, this one, we know what it represents. The constant loss. We have got our constant loss there. So we are worried about above from A to F. In between, that is where the point E is supposed to lie. That is where we go now to the idea here. They told us that the stator copper loss is equal to the rotor copper loss at standstill, because this is the part of what? Our standstill, AF. Remember, AF is our total copper loss at standstill. So when they are equal, these two, meaning to say E is in between. So it means AE is equal to from E to F. So E is the midpoint. It is the midpoint of what? Of AF. So we must measure the length of AF from A to F. How many? According to mine here, it is 18. All right, not 18, but something like 10,9, 11 centimeters, 10,9. This is according to what I'm having here. So guys, yours differs according to the exact value that you're supposed to have. It was supposed to be 9 centimeters, the wall of AF, 9 centimeters, then half of that 9 centimeters, which is 4,5. But according to this one that I'm having graphically, remember, we were zooming in and also zooming out. So half of that one is 5,4, somewhere there. Somewhere there. Somewhere there. So this is where I'm going to have my half. Somewhere there. So in between, halfway. So it must be half of that. This is approximately, all right, approximately somewhere there. So you must take half. You measure and you take half. So according to my presentation that I had, it is supposed to be 4,5 from this, supposed to be 4,5. So I don't know what you're getting, guys, from yours. It must be 4,5 centimeters, this one, and also 4,5 from E to F. So from A to E, 4,5 centimeters, from E to F, 4,5. So maybe yours, it's 4,6. Maybe yours, it's 5. We do, guys, you work with the measurement that you're taking. So also the comment section is there. Let's communicate and see the values that you're getting. With the point E, so this one it's midway because we are told about the losses, the rotor copper loss being equal to the stator copper loss. That is why E is in between. If it is not like that, you must have the proper way of finding E. We're going to do that one with a specific question. So that is it. We can join from our point O bar to point E. That line is very, very important in our calculations as it represents the torque line. So that line is our torque line. That is the major part. So we have got the torque line from what? O bar to E. From O bar to point E. It represents the torque line. From A to E, rotor copper loss at standstill. E to F, the stator copper loss at standstill. F to G, the constant. I talked about this on our introduction. So that is it. At this point, we need the last part now of finding LK after you have got drawn your vector O bar to E like this. So another way, condition 2, is when you are given the stator's phase resistance, of which we are not given. We are going to use this method. I'm going to explain it when we are having such type of a question. So that is it. We have got our torque line. Now, the last part is determination or finding and to draw the line LK, which is from the main condition that you are given. What is our main condition? Let's go back to our question. All these that we are supposed to do, determine the following from the circle diagram for what? For maximum output condition. Maximum output. So we go back now to each condition, guys. It has got its own properties. For a maximum output, this is what we are going to need. If it was for a full load condition, you're going to use this. So what I'm going to explain, you can even use it, guys, and just follow these steps. You can even do these ones on your own. You can even do the last one, which is here for the maximum torque. You can even do this one, guys, on your own because the stages are just a little bit similar. You can follow the steps. Like if you follow these steps, you can actually understand what is happening. So in our case, we are dealing with what? A condition for maximum output. So to draw this line for a maximum output, they are saying here, these are the steps that you're going to need. Extend the perpendicular bisector of the output line to cut the semicircle, of which in our case, it's already extended. This is our perpendicular, this one, to cut the semicircle. Remember, this is our semicircle. So as we can see, it cuts the semicircle at this point. In our case, there's no need to extend. But if yours, it is not at the semicircle, you must extend this line until it meets with what? With the semicircle. Okay? Let me just remove one or two here. There's another part that I'm just gonna remove. All right, well, let me just leave it because it might affect us at the end of the day. It might affect us at the end of the day. Let's just leave it as it is. So you have extended that one. Label this intersection point L, where your perpendicular bisector meets with the semicircle. Label that point L. So we are going to label the point L. So this is where we are having our point L at that intersection. We call this one L. So along this line, what is going to happen when it is of a maximum output? From this point, guys, you just draw a line perpendicular to the horizontal axis. That is it. From that point, just draw a vertical line. It must be perpendicular to the ground. That's for a maximum output. Only that. Another condition has got its own properties, but this one, it is saying where we have got this point, we must have perpendicular, just like A to G. There's no adjustment. There are no further adjustments on this one, guys. It must be what? Perpendicular. So you must measure that one at what? At 90 degrees to the ground to meet the horizontal axis. So at that point, take a vertical line to the ground. From that point to the ground. This is what they say. This is what it means. From the given point L to the ground, this horizontal axis, that line is called LK. From L to what? To K. So that's L to K. So this line LK that we have just drawn, it gives us a lot of points along it. Those points are very, very important. So we name them. The points are taken. One, this one, guys, is not important. This one from the origin, this one that is in red, this one. You do not label anything on that one. You label from this O bar, this one. So from O bar, what is it that we have? Along the output line, that is where we have got point M. along the output line where these two meet, a point M, or bar along the torque line. That is where we're going to have the point N. From this point O bar along the referred line, this one, this line, that is where we are going to have the point J. Just like that. So that's L, M, N, J, and K. And remember what I said before, in between this one, from J to K, from F to G, it is exactly equal. So that's our diagram. You done? That's your diagram there. You can have this diagram in this presentation. You can have it in that way. Understand your diagram. Understand everything of that diagram. It is very, very important in our case. So this is it, guys. I just hope. All right, the last part is to join. Let's join from O to L. This line from O to L, it represents an important line to be considered also. So we must also just have that one, O to L. Let's join that one. We're gonna need the measurements of that OL, just like from O to A. Okay, that's it. That's it. Just like that. So this is the basic idea, guys, of what you must have. This is what you must have. So anyways, here on my graph is because, guys, like I said, I'm extending. I take this graph, it's bigger. I take this one, it's smaller. So at the end of the day, it might affect my measurements. So I'm going to use the exact measurements that I obtained from my preparation. You use the values that you're getting. If you're getting a little bit, maybe it's 4,4, use those values, guys. Do not change your values to mine, okay? So this is it. We are done with our circle diagram. So we are going to see other questions because as we can see here, as we can see, there are other conditions for full load and also for maximum torque. So guys, make sure that you join membership so that you do not miss any of the classes that we are going to be having. I'm going to do other classes on membership. All right. So the first question after this was now to calculate or to determine the line current. So I stated these, all right, if you still remember on our introduction, where I was talking about these, I said you must know everything about what you are to calculate, the presentation of what you are given, and what you are to calculate. So the line current, all these presentations. So the line current is represented by what? By the vector OL. That is our vector OL at the end. So if we take where vector OL is, it is this one from O to L. You measure that line, OL. You measure that line, okay? So that's the condition of our line current. So you measure that. So our line current is equal to vector OL. But as the vector now, remember 1 centimeter represents what? 5m. So you must multiply by the scale because you are saying OL, it's a distance. You measured that OL. It is, according to my graph, guys, the exact one, it was 13,2 centimeters. So you measure that. You multiply by the scale, 5 amps. So 13,2 times 5 is going to give us what? 66 amps. So that's the whole idea, guys, that you are going to have. Wherever you're given that vector on a product, remember I talked about that on the introduction, guys, you just multiply by the scale, all right? Then the constant losses, we are now talking about the power there, but the power for the what? For the constant losses. So constant losses. There they need like everything. So that will be in this case, the constant losses, the formula is also given, or we can take it. Remember the constant losses, if you have forgotten, guys, FG or what, or JK represents your constant loss, but we need the exactive power. So the formula there for the constant losses is going to be this one, square root of 3 times, we're going to use JK there because the JK is the one for the constant loss. So guys, you just use according to your textbook, the way that you are given. So that's square root of 3 VL times what? Times JK. So the JK is a vector. We must take the exact value. So remember, our voltage from the properties that we're given, the line value is 400 volts for that three-phase. So that's the idea there, right? So this is 400 volts times, you measure from J to K, you measure it from J to K. So if you were to measure that one, it was going to give us 0.5 centimeters, 0.5 centimeters, something like that. So that's 0.5 centimeters, but we must multiply by the scale. Remember, each centimeter represents 5 amps. So we multiply that way. So that was going to give us 1732,051 watts, which you can even convert to the kilowatts. Okay, so that is our constant loss. We do the same thing on the other part. So there you just need your formulas, guys. All those formulas, they are exactly given. The stator copper loss 8 stand still. Remember what you're dealing with there at stand still. So that one, the stator copper loss. All right, the stator copper loss at what? At stand still. So this one will be square root of 3 times the line voltage times which part represents the stator copper loss at standstill. The stator copper loss at standstill is what? Is EF. So you multiply by what? By EF. So you multiply by vector EF. All right, so that's it. So that's square root of 3 times 400 times vector EF. According to the measure, you measure EF, how many centimeters there? So remember we said 4.5 as we measured before. So that was 4.5 centimeters. But we need the exact value. Each centimeter is 5 amps. So multiply by the scale, 5 amps. So that was it. It was going to give us the stator copper loss of 15,588,457 watts, which you can convert to kilowatts. Again, it is in your hands. Conversion there, it is in your hands. Another question, it was to determine the rotor copper loss. So the rotor copper loss, when we are not given to say 80 stand still, take note, they did not mention to say 8 stand still. They did not mention that. So when they do not mention, you work along the line LK from L to K. All right, there was a part here. Okay, this one where I explained this one. The stand still is along the line what? AF. Whereas the other part is along this line L to K there. So they are referring to the rotor copper loss. So in order for us to have the rotor copper loss, you must work with the section what? MN for the rotor copper loss, MN here. At any condition, they did not mention there to say at standstill. So you use at any condition, like I said on the introduction. So you use what? MN. So you're going to multiply by MN. So that's it. Let me just write it here, guys. Rotor copper loss is going to be square root of 3. The voltage times, we said what? MN. Going to use vector MN. So that's it, square root of 3. The line voltage, remember that was 400. You measure the length of M to N here, M to N. So that was going to be approximately 1,5 centimeters. If you measure properly there, that's going to be 1,5 centimeters times the scale. Our scale is what? 5. So you multiply by that. So that was going to give us 5,196,152 watts. So that's it. We have got our D on that part. So that's our rotor copper loss at any given condition. The rotor output, again, we can trace it from the diagram. Where the rotor output is, remember from that line L, the rotor output is affected by what? Line L to M. That is the part of the rotor output. Line LM. So you must measure from L to M, you measure that distance. This is the distance that you are going to need here. So it's square root of 3 line voltage times what? The line LM, the vector. So that's it. That will be square root of 3 times 400. We measure. So measuring that line, it was going to be 6,3 centimeters times the scale of 5. So remember, whatever that you measure times the scale. So that was going to give us 21,823,84 watts. You can even convert to the kilowatts. So just like that. Then the other part, the percentage slip on F. The percentage slip. So in order for us to have the percentage slip, we can calculate it from the rotor copper loss over, so it's actually supposed to be rotor copper loss over what? The rotor input. Over rotor input times 100%. So remember I discussed about these guys, rotor copper loss. When you say about rotor copper loss, if you trace it from our diagram, that is our MN, rotor copper loss, right? Where is that one? Here, MN. The rotor copper loss, if you take here, this is MN. So you can just take that length of MN as it is, all right? So rotor copper loss is MN over what? The rotor input. The rotor input, you're combining everything from here to N. So that's LN. This is our rotor input, LN. Just like that. So note the diagram, guys. If you understand that diagram from our introduction, you see everything will be just direct. So there you can just take the length. If you have got these values, let's say you calculated them as the power. You calculated rotor, copper loss, rotor, take them because we calculated them. Or we can just use the diagram. From M to N, you measure that length, of which you talked about this one. We said is what? 1,5 centimeters. You measure that. From M to N, approximately it was 1,5. So guys, use what you're getting from your measurements. From your measurements, that was 1,5 over Ln. From L to N, we talked about Lm before. Lm is 6,3, this one. And this one, it's 1,5. So 6,3 plus 1,5. It's just going to give us 7,8. So that's 7,8. Ln. The whole of Ln is what? 7,8 times 100%. Just like that. So that was going to give us 19,231%. Or you can use the exact values for the power that you calculated. Still, you're going to get same answers or same values for this one. So this is how these questions might be given, as you just have to be very, very careful as you work with the question, the information that you're given. You have to be very careful. Try by all means to understand, especially here, the starting part. Phase angle versus corresponding vector, which was supposed to be the current for that part that you're working with. But we cannot indicate the current, so we must have the measurement of the vector representing that current. We must have a measurement, which is now vectors from O to O bar, from point O to what? To point A with their corresponding what? Phase angles. So let's revise as many questions as we can. But as we are doing the revisions, I want you guys to work out this part as an individual. Just also try to do questions where they talk about the maximum torque. Just try to go through these steps that you are given, and your diagram will be like this at the end. Okay. And also for that last condition for this full load, if you are dealing with a full load, follow these steps, you're going to have your diagram like this at the end. So let's try. If we do not understand them, let's communicate. That's the purpose of the comment section. Let's communicate and also be part of membership so that we can have these questions explained in any other way that we might need to understand them.